All right. Hello, everybody, both watching via Zoom and here in the room with me, and also those who are watching the recording. Really glad to have all of you here. We're going to talk about some really cool, really important stuff about manufacturing at UCLA. So it's on. Yes. All right. So what is this workshop for? We're having this workshop because it is very important. A lot of people who are here have not been on campus for a year before this. And even for those of us who have been on campus, a lot of things have changed in terms of manufacturing from what it was or the previous year that we were here. So we're going to talk about that. We're going to talk about what's changed, and we're going to talk about basically how do we make things at UCLA and what are our methods, how do we use them, where do we find them, all of that good stuff. So everything in this presentation, there is more detail about it in this document called the Full Machining Resources document. So we've put a list of everything there. That's a really great place to look if you want more details about any of the stuff we're going to talk about. But it's presented in a nice sort of condensed form here, so it's easy to get a sense of. Okay. So the first thing we're going to do is we're going to talk about the various locations on UCLA campus where a lot of these machines are located. I'm going to talk about them, and then you'll hear us reference them later on when we're talking about specific tools. So up first is ASME Lab.
Right, so the ASME Lab, you love it, you know it, you've probably been there. It's 2730C, Boelter Hall. If you want to use some of the machines in there, you can talk to any of the officers, but especially you should talk to your project leads. And then after that, you can talk to me, Alyssa, and Aaron. And you can find the contacts there. I mean, you guys know us. Contact us through Slack, through Discord. We'll respond if you have questions about this.
Yeah, one of the most accessible of the spaces we're going to talk about. I would say the most accessible, because basically you can go in there whenever you want. Yeah. All right. So next up, we have the Boelter Makerspace, also called the UCLA Engineering Makerspace, also called the Boelter Innovation Lab. A little bit confusing about that, but basically this is the prime makerspace on campus where we have access to all of the tools in there. It's a collaborative workspace. It's located, there's two locations. It's located in both downstairs first floor Boelter Hall and the second floor Boelter Hall. So the downstairs space is where most of the equipment is located. That's Boelter Hall 1805. And then the upstairs space mostly used as a classroom for E96 classes, but there's also some electrical tools in there. We're not really going to talk about the electrical tools because we didn't categorize that under manufacturing exactly, but you're interested in that, you can always go and ask someone who works there about that. Yeah, so there's staff in that space. I didn't put the hours on here, but we're open weekdays 9 a.m. to 6 p.m. And if you have a specific question about something, you can contact the supervisor, who's called Jacob Schmidt. There's his email there, so we'll talk about that as well.
So another resource that we're supposed to have access to is the machine shop. Machine shop is closed now, though. They found that the floor is bad. And so they're working on it.
Can't have that.
At the town hall last week, Professor Fisher said that it could potentially be opened by spring quarter, but I think that's unlikely. So usually it's right next to the Boelter Makerspace. It has a big yellow door on it.
It's the same room number.
Yeah, same room number.
But it is not the same room because the door is yellow instead of blue. That's all the guidance I can offer.
There are some machines that they set up for MAE 183 in the MAE lab space that we can use. And we can have access to some of the other equipment if we ask, but it's extremely limited. So if we really got to do something, we can, but it's not ideal. And these are the contacts. Ben Tan is the MAE lab manager. Miguel is the senior mechanician. It doesn't sound like a real word, but it's what his job title is. He can definitely get some stuff done for you. And then Travis is the welding guy. Yeah. I'll get to that later.
So we also have the Olympic Makerspace, also closed. This was supposed to be open this quarter. It was open earlier this quarter. They are also having some building issues where no one's allowed to be in there right now. So this is another big sad for us because they have some really cool stuff in there that we cannot use. So it's located up in Olympic Hall, which is the new one of the new dorm buildings that was just built. It's there on the 4th floor, which is like the way that you enter the building to the 4th floor. This is the email of the supervisor. If you want to talk to him about anything specific, He's a really nice guy. However, it's just because the space is closed, there isn't really that much wiggle room.
Okay, so on this one and last one, we've included all the resources that we think we're going to be in these spaces. So the Olympic Makerspace is in orange, and we go back.
Oh yeah.
The machine shop stuff is in red.
Yeah, so if you see those colors on any of the tools, that means it's located only in that space. So if you look at it and you're like, ooh, I want to use that, just know that you can't.
Well,
so yeah.
For the machine shop stuff, you might be able to, but not in high capacity.
Yeah, so we're including information about all the tools in these spaces just because we do expect them to open up pretty soon at some point.
At least
we want you guys to know what's in there, but just know that you can't use it right now. All right.
Okay, now we're going to
First
move on to the types of machining. So the first set of tools that we have is material removal machining. Material removal manual machining.
Yeah,
that's what it is. Okay, so first machine that we have talked about is the mill. It's for removing material from a flat square face. So it's good at taking pieces of square, like rectangular prism stock, and making features in them that are all perpendicular to each other. So you can see there's kind of two operations we can generally do. This one's usually on the side. We can either face the top or face the side. So that's only reducing. That's only making stuff in. And again, that's perpendicular to each other. It's important that opposing faces must be parallel. So we can do things like machine off the top of a cylinder or the side of a cylinder, but the opposing faces, to be able to put it in a vise, must be parallel. We can also drill with the mill. We'll get to that next. The mill is good for plastic, aluminum, and steel. We have a mini mill in the ASME Lab, which is pretty good. We can do a lot of stuff. It has a digital readout, but it doesn't work very well. And there's a big mill in the machine shop we have access to. Its digital readout is much better, and it can just take off more material. So if you're looking to machine some like serious skill parts, that's what you would go for. Drilling. So this is for making round holes. It's either making holes that go to an endpoint or go all the way through. There's three ways to do this. We can use hand drills. So this would be for parts that are either really big or that we don't need to be that precise, or generally that are wood. The drill press, we have a small one in the ASME Lab. There's also a big one in the machine shop, and there's probably going to be one in Olympic as well.
Yes.
But we didn't include that here. It's good for, the drill press is good for big flat parts that you can't secure well in the mill vise. You can just kind of clamp them to the table of the drill press, very easy, especially for through holes. Ours has a maximum hole size of Z, which is 0.413 inches. If you want to go bigger than that, you have to use the chuck that's on the mill. So then we have, which brings us to the mill. We have up to a 1/2 inch drill bit. I think you can take a little bit bigger than that, but not too much. The mini drill press doesn't have speed control, which is very important if you're actually trying to drill big holes, but the big ones do. So just keep that in mind. Yeah, big drill press in the machine shop. Lathing. So this is for machining cylindrical parts. What we can do is we can turn them, which is reducing the diameter. We can face them, which is reducing the length. We can drill with the lathe to the end of it. So you like the stock, you put drill chuck in there, and you can drill all the way through. Boring is another operation for making bigger holes on the inside of parts, only through the center axis, obviously. We have a mini lathe in the ASME Lab, which can go up to 3 inches. It's for plastic and aluminum. And then the big lathe in the machine shop, they can do much larger parts, much larger holes, steel. You gotta be careful with trying to machine purpose-made shafts. They're usually cold worked and hardened, and they can break machines. So don't do that. Last manual machine, taps and dies. This seems very simple, but it's important to know that we have. It can either create threads on the inside of a part or the outside of a part. With the tap, we'll do the inside. Die will do the outside. These are for aluminum, steel. If you're You can do it in plastic, but at that point you might as well just 3D print it. We have a lot of tap sizes and a lot of die sizes, at least imperial ones, but you should check first that we have it. If not, if it's for a project, we could probably get it, but just check first.
Yeah, it's still better to tack onto the print rather than the plastic.
Oh, I meant die.
Oh, for dies?
For outer ones.
Yeah. If it's big enough that you're making external threads in the plastic part, you can probably print them.
Yeah.
All right, next up, we got CNC machining. So this is where the computer does the work for you. So it's a lot of the same tools, but it's controlled with the computer instead of you controlling it by hand with the cranks and stuff. So this allows you to create a lot of really complex, different, interesting geometry. So first up is the 3-axis CNC mill, so called because it has 3 degrees of freedom, 3 axes in which it can move. So it can basically move over a 2D plane, and then it can move up and down as well. So similar to how a 3D printer usually moves. So this means, or the regular mill. It's just like a regular mill. We'll talk about a different number of axes later. So this is, it's controlled by computers. Computer controls the way that the tool is moving, so you can create these precise curves. You can create more precise levels. You don't have to worry so much about messing up while you're making the part yourself.
Yeah.
However, to do that, it requires you to use CAM software to set up the computer to do that, which can be a challenge, as we found out in 183 this week. It's a huge challenge, more than I thought. So make sure that you know what you're getting into if you design a part and you think, oh, we can just put this on as CNC.
Yeah.
It will be a bit of a challenge.
Well, they'll be able to help you with the makerspace. I think that might be easier.
Eventually.
Doing it through the MA department is going to be a pain.
Yeah.
The makerspace might be able to.
So yeah, so this tool currently is only in the Olympic Makerspace, which is closed. They have a pretty small 3-axis CNC. There's one, or I think there's several in the machine shop, also closed. So then our only option for this currently is through the MA department. They have some not in the machine shop space exactly, but in spaces that are controlled by MAE. If you want to deal with that, it's going to be kind of a lot of a pain.
So the nice, so just to make one thing clear, what this can do that the other mill can't is this can make curved parts. Like I said, that all the mill parts that you make have to be perpendicular to each other. This doesn't have to be that. This is one of the best ways of making holes that are too big to drill. It can also drill holes in precise fashion because it's a computer.
Yeah.
Like you can't sit there on the mill and precisely slowly go around. Trust me,
using an X and a Y control, you cannot make a perfect circle. But if you've ever used an Etch-a-Sketch, you understand the principle behind this.
Yeah. So this can. So yeah.
Yeah.
It's not ideal, but if you have a good reason to use that kind of thing, this would be how you do it, or the other CNC machines.
Yeah. So we're going to talk about more. All right, moving on to other things that you shouldn't do unless you absolutely have to. The 5-axis CNC mill, also located in the Olympic Makerspace, which is closed. So they have a really very small one that's called a pocket NC. So it's like 4 by 5 by 3 inches, but actually it's more complicated than that because it really depends on the geometry of your part.
And also that's 3 of the axis of rotation, but it has 2 more.
Yeah.
So it's kind of that.
It's super cool. The tool, as you can see, is rotating relative to the part. It's not staying perpendicular to the part. So you could theoretically use this to create some really complex, really interesting curved surfaces, angled surfaces, all of this stuff. The actual CAM process to do that, I can only imagine how terrible it is. I have not ever done it. So once again, know what you're getting into and know that we currently don't have access to this. If you want to use it, you'd have to talk to Makerspace staff. You'd have to do a bunch of stuff to figure that out. All right.
Okay, traditional cutting tools. We'll try to move through these a little bit quicker because they're less important. Okay, vertical bandsaw. This one is actually pretty important.
Yeah.
It's best at making straight cuts on large flat sheets. So if you have like a big piece of 2 foot by 1 foot aluminum and you want to cut it in half, this would be how you do it. It's also pretty good at cutting bars and rods, but for the small, okay, so there's 2 that we have access to. We have small ones that are in the Boelter Makerspace. and they can cut plastic, wood, and very thin aluminum. When I say very thin aluminum, I mean very thin aluminum. I once cut a 1-inch shaft in there, and I think I broke the blade on it. So it's pretty bad at cutting things like that. There are other tools that I would suggest doing small pieces of work like that. We'll get to them next. But yeah, very, very thin sheets of aluminum you can do on this one. The big bandsaw, much better. It can do a lot of stuff. There's only one set up in the machine shop that can do steel, but the other two can do aluminum. And that's good. You can cut, like, I think Mitch cut like 3-inch stock for fade in the past, so you can definitely do it. There's only one that can do steel. You have to make sure not to use cold worked or heat treated shafts. This is a big thing that they'll tell you. If you try to go in there and say, "Can I cut this?" they'll ask you that question. So can't cut those things in there. Okay, horizontal bandsaws. This is for cutting non-sheet parts. It'd be very difficult to cut a sheet with this just because of the nature of the tool. It's good for cutting rods and shafts, so things that have a significant cross section, and 80/20. There's a small horizontal bandsaw in the ASME Lab that's up to, can only do aluminum and softer materials. It's up to 1 inch thick. It's not very good, pretty bad. There's a larger one that can do aluminum and steel. It's probably better, but just the nature of this tool isn't great. What I would suggest that you use instead is that you use the chop saw. So this is, okay, unless, if you're cutting metal, the chop saw that we have in the Makerspace can only do aluminum and steel. Because the blade that it has is abrasive. So if you tried to cut metal, it would burn.
Or no, cut wood.
If you try to cut wood, sorry. If you cut metal, it will like chip away at it. But if you try to cut wood, it's just going to burn. Or plastic won't work either.
The other day, and we all learned something because it was very clear that if they had continued to cut this whole piece of wood, they would have started a fire because it was actively burning the wood and like charring it and making a lot of wood burning smell.
Then slice it.
Instead of actually cutting it through.
There are wood chop saws, and we could get a wood blade for this chop saw, but we don't have one right now. I think they're planning on having one in Centennial and Olympic, but we don't quite know. So if you want to cut like big planks of wood, the bandsaw is your best bet, but difficult to do. Yeah, it's much better than the bandsaw. If you got to cut, again, metal, aluminum or steel, you could use the angle grinder. Much better at cutting steel than it is aluminum. This is good for if you got to cut thin pieces of material in a pinch. Doesn't work very well, but you can do it. You could cut big pieces of wood with the jigsaw.
Yes, that's what I would recommend.
The jigsaw, you can cut really big pieces of wood or plastic. You'd have to create some kind of a jig, as it implies, to help you cut it straight. It's just this kind of hand tool. It's a bit like a reciprocating saw where it has a blade that goes in and out. So it's very controllable, but it's not very precise. So the cuts, but for the nice thing is that the cuts don't need to be straight. So if you need to cut a circle out of something big, you could do it with the jigsaw.
Not a very precise.
Not a very precise one, but you can do it. Okay, hand cutting tools. Hacksaws. There's some in the ASME Lab. There's also some in the Makerspace. These are good for plastic and wood and aluminum. Like if you really gotta cut something and you don't have any other option, hacksaw will do it. It's just gonna take a while because you have to sit there going at it. Tin snips are good at cutting thin metal. This is including titanium. So this is one of the only ways we can cut titanium. If you see, if we don't mention titanium on a part, that means you can't do it. You might be able to get away with drilling it, but really we don't have a good way of manufacturing titanium. Tin snips can at least cut it into smaller sheets. If you're gonna cut big pieces of plastic, you could use the X-Acto knife or the box cutter, or just cardboard. Scoring it and snapping it is a pretty effective method of cutting. Acrylic, it doesn't work as well with polycarb, but it works pretty well for acrylic. We also have a PVC cutter up to 1 5/8 for cutting PVC pipes.
Yep. Starting and finishing. So this is a very useful process. A lot of times when you're making something, it comes down to this because you have something that almost fits and doesn't. And that's when you gotta explore the various materials in this section. So by hand, there's a couple ways you can do it. You can use a file. These are tools made out of metal. So they'll just, basically you can just scrape against your material. It'll remove a small amount. It makes parts smoother or removes material. Sandpaper is what you'd use if you want to go and you want to make a finer finish. You want to make things really smooth. Basically, file to sandpaper to finer sandpaper is just stepping down how smooth you want your surface to be.
Increasing your grit.
Increasing your grit, yeah.
Yes.
Higher grit sandpaper is finer particles. It leads to a smoother finish. You can do this on basically any material. It's going to go faster on some materials than others. It's going to go faster on wood than it is on steel, but
it's not going to work well on materials that are going to shatter, like glass or acrylic.
Yeah, you got to be careful because you're applying quite a bit of force to it. You have this repetitive motion.
But it would work.
Yeah. So if you want something a little more powerful, there are a couple different options for power finishing. My favorite tool ever in the whole world is a Dremel. I will tell anyone that. So a Dremel is just this basically little tiny hand drill. It just has a spinning end. You can put all kinds of different ends on it. So you can put sandpaper ends on it. You can put a drill end on it. You can put like a little grinding wheel or a wire brush or all kinds of things. So that's really good when you want to remove some material from a specific spot. You can just use this tool to drill it out a little bit, or if it's somewhere that's hard to reach. Belt sander is also really useful. It's just the same as sandpaper. It's just sandpaper in a loop that goes really fast. We have several of them in the Boelter Makerspace. There's big ones in the machine shop.
Well, it's kind of like sandpaper, except it does almost the opposite. The belt sander takes off a lot of material, whereas sandpaper you can barely take off any at all.
I mean,
especially the small ones. The small ones don't do very well, and the ones in the makerspace can't use steel. But the big belt sander is one of the more dangerous tools that we have at UCLA. It'll definitely take off. That's the one that they really warn you not to wear gloves on. It will just go right through your finger. Yeah. But it will also go right through your aluminum part pretty easy.
Yeah. It can take off a good amount of material. We use it a lot to deburr edges. So if there's rough material on edges after you cut it with the bandsaw or chop saw, you just basically put the edge up against the belt sander for half a second and it'll take off that whole burr. It'll give you a nice finish, chamfered edge. So that's useful. And then the angle grinder, as mentioned earlier, can be used to cut, but you can also use the grinding wheel instead of the cutting wheel on it. So that's also a way to do that.
Yeah, that one's just for metal.
Just for metal, yeah. All right, sheet cutting. So this is similar to some of the other tools we mentioned, especially the CNCs. However, this is specifically if you have a part that is a big, thin, flat sheet of something. Like this and stuff. So talking about the laser cutter, the laser cutter is a tool which we have in both the Boelter Makerspace and the Olympic Makerspace. It uses a computer-controlled laser to burn or melt the edges of your part, and that's how it cuts out. So it's capable of etching as well as cutting. However, because it's using that method of burning or melting, it means you cannot use metal. You can, unless it's a very, very thin sheet of metal. So we use this to cut through primarily acrylic plastic and plywood and cardboard. You cannot cut polycarbonate, MDF, which is like a fiberboard, metals, or anything that's really thick. So it has a bed size of 18 inches by 32 inches, so it's pretty decently large for anything you want to do. The finish on the edges is usually really good. If you're cutting thicker wood, it'll burn the edges a lot because you'll have basically a whole edge of charcoal around your part. So anything like that doesn't do great, but thin plastics, thin wood, it does amazing. Yeah, it's also super fast. So it's so much faster than creating this finish on most of the other materials. Yeah. No, it's not changing here.
Okay, so the next one is the Waterjet. This one's through the MA department. It uses a stream of water mixed with abrasive to cut through metal. It can do plastic. Specifically, it can do polycarbonate, aluminum, steel, up to an inch thick, and titanium. So that sounds very impressive. Its max size is a foot by a foot. But okay, if you try, this is kind of true for all of these CNC machines. If you actually tried to put something in there that was a foot by a foot, it wouldn't be able to do it. This is especially true with the Waterjet. It will give you an error where it will hit the edge and not be able to do it. So you really need to, for the Waterjet, you really need to be like 11.5 by 11.5 for it to work. Jet makes it's a decent finish. The tolerance isn't great because the thickness of the jet isn't accounted for very well. So if you're actually trying to make very precise holes, it won't really do it, but you can make bigger holes with it. You can also go through a lot of materials, as you said. It's extremely slow. If you're like, should I make this part out of polycarb or should I make it out of acrylic? If it's really that much of a choice and you can make it out of either, you should make it out of acrylic so that you can cut it much faster on the laser cutter and not have to deal with the Waterjet. Currently, the draining system is not functional. So this means that after you finish, you need to suck all of the water and abrasive that you just put in the Waterjet out with the shop vac and throw it down the drain. This is very annoying and very messy and takes a lot of time. I told the department, hopefully they'll get it fixed, but who knows? And the reliability on this is generally very low. So this machine can do a lot, but it really sucks.
Yeah. Speaking of another machine that can do a lot but really sucks, we have the plasma cutter. So we just got the plasma cutter at the Boelter Makerspace, specifically to cut plates out of aluminum. And guess what it is really bad at doing? Cutting plates out of aluminum. So it uses plasma. It basically superheats a jet of air, which is kind of similar to how the laser cutter works, by using that heat. But it's actually hot enough that it melts through metal. And it can melt through really substantial quantities of metal. It can melt through, solid steel up to like 1/2 to 3/4 of an inch thick. However, it is this terrible surface finish on any of those cuts. So it's basically all the molten metal in those cuts creates a lot of burr, creates a lot of, rough edges. Basically anything you're making, it requires post-processing. So if you take that part that you just cut with its rough edges, and you have to put on the belt sander to sand it out, you have to drill out all the holes, because the holes are going to be totally the wrong size and shape. It's really, really kind of a huge thing. The price to this it's really big, 4 foot by 8 foot. So if you have a massive piece of metal, you can cut stuff. It cuts through aluminum, cuts through steel, and it is super fast. It's pretty much as fast as the laser cutter for things that are much, much more difficult to cut than what the laser cutter's cutting. So it's the best and quickest way to cut parts out of metal, but it just be aware that it's not going to be accurate.
There's also a minimum hole size that it can do.
Yeah.
I think this machine is very new. We're still trying to work out the kinks in it.
We tried to cut some holes, and instead of cutting the holes, it cut bigger holes.
Yeah.
And then if we tried to undersize the holes, it gave us an error that the holes were too small.
Yeah.
So the minimum size is like 0.14 inches or something.
Another note is that since this machine uses melting, like the laser cutter did, the alloy matters. So you can't just throw a random piece on there, because we tried cutting what we think is 2024 on the 6061 setting, and it didn't work. So you really got to know what alloy you're putting on there, and there isn't a setting for 7075. So
there's a general aluminum setting that we have not tested.
What does that mean? So you're probably limited to 2024, 6061, and mild steel, or stainless steel.
Yeah.
This is a machine that we think can do a lot, and we hope doesn't suck. We're very excited about it, but we don't have access to it because it's in Centennial, or Olympic, sorry. This is the router. So this is kind of like a 3-axis mill, except it's flipped. Instead of the part moving relative to the mill, now the mill moves relative to the part. So it's the same 3 axis, X, Y, and Z, but you can use a much bigger sheet. So because as you can see, the whole thing kind of traverses over the material. The max size is 36 by 24 inches. We can do plastic, wood, and aluminum. Again, we don't really know what the CAM process for this is, but I can't imagine it's that bad. This is probably going to be one of the easier machines to CAM with. This has, out of all the sheet cutting machines, this one should have the best finish and tolerances. It can make very large and precise holes because, again, CNC. And it's using an actual mechanical tool instead of some kind of other cutting method. This is the only one of these that can cut to depth. So if you're like, okay, this part I want a water jet, but it needs to have like a step in it, or it needs to have multiple layers. You can't do that. The water jet and all the other machines we just talked about only go all the way through. This one can go to depth. As you, I mean, you look at this GIF, you can see it's doing it because it's 3-axis. I think this will be faster than the water jet, but slower than the plasma cutter, but it's hard to tell. Especially for, depending on the thick, it really depends on the thickness of part you're cutting. The cons is it uses more stock than you need to, because instead of cutting a very thin line around the outside, it needs to cut, the thinnest line that this thing can cut is with the thinnest tool. So it needs to make a pass around the outside so your part comes out. So unlike the other tools, for this one, the inside surfaces must be rounded because you're cutting with a round tool. On the outside, you can make a square cut with a round tool, but on the inside, you can't because you're cutting with the outside edge of the tool always. We talked about the camera. Okay, next one.
All right. Next up, we have one of my favorites after the Dremel. We have additive manufacturing, which is basically a fancy way of saying 3D printing, for those who don't know. So we have a lot of different kinds of 3D printing, and if you have never looked into the different kinds of the different methods of 3D printing, I'm going to go over that as well. So the first up, we have FDM 3D printing, which is how you most conventionally think of 3D printing. That stands for fused deposition modeling. So what that means is it's taking a thermosetting plastic, or a thermoplastic plastic, and it's heating it up and it's extruding it out of the nozzle. It's basically taking this long string of plastic and it's drawing out the shape. So the computer is guiding it to create a shape, draw it out, and then it builds up layers to create your finished part. So this is a very good, like cheap, pretty fast, affordable, accurate, more or less way of making a part, making a prototype or a final part. So the two printers that we have are, basically the two that we have access to, there may be other ones somewhere, is Prusa. Prusa is a manufacturer of 3D printers. Prusa original, like i3 MKS. We have a bunch of these at the Boelter Makerspace, as well as at Olympic. And we have one in the ASME Lab that is for ASMEs. So this is a very reliable, very high quality printer. It prints primarily in PLA plastic, but you can put a couple different materials in it. And it's about 10 by 8 by 8 inches. So it's like a decent size for anything you're going to print. The one disadvantage is that you cannot print in ABS plastic, which is a slightly stronger variant. You can only print ABS plastic to use the next printer, which is called the Raise 3D. So this one has a much larger build volume. It's almost a complete cubic foot build volume. We have several of them at Boelter Makerspace, and they are just not very reliable. They're not very good. They break all the time. You have to print a raft under your part, so it usually comes out kind of bad. But what you can do is print two colors, print larger, or print in ABS. So if you need any of those things specifically, you should use this printer. If not, you should use the Prusa for everything. All right. Next up, we have SLA 3D printing, which stands for stereolithography, which is one word. So I don't know why it has a 3-letter acronym, but it is stereolithography. Very cool, very interesting method of doing it. It basically takes a laser underneath a bed of resin, like a vat of liquid resin, and it solidifies the resin in one layer at a time, very slowly. So it builds up upside down, as you can see. So this has a couple advantages over FDM. It's very, very precise. Like the surface will look so much nicer if you have any kind of detail on your surface. The material also is like, it's gorgeous. It's like you can make translucent. You can give it like very smooth finishes. And the parts themselves are stronger. They don't shear in weird ways because of the plastic layers for FDM.
I know 100%.
And it's 100% infill always, so it's like a solid plastic part. It's very strong. Even if it's a complex shape, it's much easier to remove the supports because the supports basically like this sort of branching structure. So this is a great way to print stuff. The only downside is access is pretty limited to it. So they have several of them at Olympic that they let people use. We have one at Boelter. However, it's not currently open for general use. You have to contact Professor Schmidt directly about it. So if you really want to, you can probably do that. If you are printing a bunch of stuff, you'll probably have to pay for the resin. Resin's about $150 per liter of it. So don't use it too much, but it's great. It's a cool machine. All right, and very last in the 3D printing category, we have SLS, which is even more exciting. That stands for Selective Laser Sintering. So they have one of these at Olympic. I'm very shocked that they have one because it is very expensive. And I don't know why anyone has a specific need to use it, but they did buy one. It's pretty cool. So this takes a bunch of very finely powdered plastic, nylon powder. It has a big vat of it. And then layer by layer, it goes over the powder and it uses a laser to melt that powder, basically fuse the powder together into your part. And then when you get it, your part's completely like unsupported because it has all the layer, all the powder is supporting it. So you can just take it out. Really good strength on these parts, really high accuracy, good start to finish. Yeah, if you went up there once it's open, you'd have to talk to them specifically about using it because I don't think they allow people to use it just whenever they want. They make them pay.
It's not open.
And it's not, well, yeah, when it's open, I said.
Yeah. This would be like something you want to make on the 5-axis CNC mill, but the 5-axis CNC mill can't do it. Yeah. The applications for this are just so extremely niche.
Yeah, I don't know why they have one. This is like 10 grand.
This is the kind of thing you use to make tools, right?
Well, I mean, maybe it's plastic. It's
right. Other tools. So we have some access to welding. So what welding does, pretty obvious, it creates a permanent joint between two flat faces. So this is not a permanent joint between two flat faces, but it kind of is because they have to cut that pipe flat first. It's easiest for steel. We can do aluminum of similar alloys. I don't know exactly all the details about this. We can definitely do, I think we probably have both MIG and TIG welding. However, UCLA, we have some exciting stuff. UCLA is, one of the professors at UCLA, Professor Lee, his lab developed a nanotechnology welding stick that you can weld 7075 with, which could not be done before. So if you really want to weld 7075 for some reason, like flagship combat robotics, Joe's working with Professor Lee and they're going to do it, even though you shouldn't really use welding in robotics at all. Yeah. For X1 people, don't weld anything. That's not a good idea. You can't take it apart once you put it together. You can take it apart if it gets warped or if you mess it up somehow. That's it. So this method is something we can do, but only if we really got it. So like steel bridge uses this a lot and racing uses this a lot because they need a big rigid chassis. We don't need that. So yeah, it's just but it's available. Cool. Heat work. So we said we wouldn't mention soldering irons, and here we are mentioning soldering irons. So we have some soldering irons. There's some in the ASME Lab. There's some in the Makerspace, as we mentioned. They're good for soldering, but they're also good for heat set inserts. So, or even screw expand inserts. So if you want to make internal threads in plastic, heat set inserts is the way to go. If you did 3-pound combat robotics, you definitely are very familiar with heat set inserts at this point, or at least we told you to use them in your updated designs. They're pretty good. We also have a rework station. What this is designed to do is it's designed to blow very hot air over chip components so that you can melt off the chip but not destroy the rest of your circuit. But it's also good at melting heat shrink. Yes. Instead of just using the soldering iron, so you don't accidentally burn it.
All right. I insisted that we have this slide because I think it's important. These are decorative tools that you use to decorate things that you've manufactured or to improve the look of something you manufactured. I put the vinyl cutter on here, so I do think we should talk about the vinyl cutter because it's really cool. This is a tool that we have in Boelter Makerspace. It cuts out stickers, and that may not sound like a lot, but when you put flame stickers on your BattleBot, it increases speed and power by up to 30%. That's confirmed. So please print out flame stickers and put them on your battle box. Yeah, it cuts out stickers. It can also cut out of vinyl material that you can heat press onto t-shirts. So you can make custom t-shirts. It's really cool. That's not for robots, but you can put a t-shirt on a robot. That would work too. Second up is wire brushing. We talked a little bit about the Dremel tools, but this is something that we've got kicking around in the makerspace. We might have one in the lab. If you want your metal surface to look better, you can wire brush it, and it'll end up with a really nice finish. It'll look shiny, similar to sanding. And then last is painting. So there are some resources for spray painting. There is a specific area you should go to spray paint, which is the paint box next to the Boelter Makerspace. And Jacob Schmidt, who supervises the Makerspace, also controls that area. So if you want to use it, you'd have to get permission from him. We don't provide paints at the Makerspace. There are some in the ASME Lab. So there's like a couple random spray paint colors and like finishes and stuff. So that is accessible.
Okay, so now we've been talking about the things we can do. But it's important that we also know the things we cannot do, so that you don't try to do them if you can. So manufacturing methods we can't do. So a lot of times people want to do sheet metal work. We have no way of doing sheet metal work. We don't have any kind of press or bending equipment.
You can cut out sheet
metal. You can cut out sheet metal, but you can't bend, you can't emboss, you can't draw it. We just don't have the capability to do those things. We've kind of touched on this, but we're working as limited. We don't really, most of the tools have abrasive blades in them instead of that are designed for metal, because that's what we mostly use and not wood blades. So just keep that in mind if you're trying to make something out of wood. You can't put a part into a CNC machine. So that's really any of the cutting machines or the explicitly CNC machines that have already been cut into. I mean, you can put it in there, but it won't be able to line up.
It won't be accurate.
Yeah, there's the true CNCs require very precise, like square pieces of stock or round pieces of stock, and the other CNCs, you're really lining them up by eye. So even getting parts cut close to the edge is very difficult. So definitely can't do that. You can do it the other way, where you can work on parts you've already cut out. That's good. You should do that instead. Injection molding. So we've had people ask us if we can injection mold in the past, and we said no. Injection molding is for like 100,000 to 1 million units. We are trying to make 3.
3D printed.
3D printed. Casting. Yeah, same thing. That's for, I mean, it might be for the same about production rate, but we don't have any way of melting the metal. Vacuum forming. Some of the labs might.
Some of the labs have
vacuum formers.
We don't know how to like things.
Yeah, we don't have, unless you like work in the professor's lab and they've given you like explicit consent to use it. Like we don't have that. It's just easier to work around, generally. So that goes to the next point. You can look into outsource something if you absolutely need to, but generally you can get everything you need to done with all of the other machines we've just presented. Yeah. Once the Olympic is open.
Yeah. All right. So this next point is a little bit more tricky to explain. So the previous was all specific manufacturing methods that we don't have access to. This is things to keep in mind when you're designing your part, geometries that we can't manufacture. So this is really important as well. So the first point is the most important: sharp inner corners in a metal part. So if you, the most common one that people try to do or consider doing is making a hexagon profile inside of a metal part. It's useful, say if you have a hexagon shaft coming from a motor and you want to put like make a wheel hub that has a hexagon on the inside. If you think about it, there's no way we can make that, because even if you had a like a really good CNC, you would always have a radius on that inner corner. So no hex profile, no inner D profile, no like triangular inside. just because there's no way to get that corner, and you need to get that corner in order to get the edges.
You can 3D print those parts,
Yeah, absolutely.
and you can like waterjet or plasma cut them, but the tolerances are going to be not high enough to actually have anything that works.
Yeah. Laser cutting is also good for this if you need just like a thin piece, but yeah.
But actually making it out of metal, you can't do.
Yeah. The second point is large, meaning long, accurate cuts in a material. So we talked about the cutting tools like the bandsaw and the chop saw and the jigsaw. Those are all ways that you can do cuts. None of them except the jigsaw are really for long cuts, and even the jigsaw, it's not going to be accurate. It's not going to actually be very straight. So if you have, say, like a big, like 2-foot plank of aluminum, and you're like, I want to cut it just down the middle, what are you gonna do?
Like you can try it on the bandsaw, but it's not going to be very good.
And it's not gonna make you happy. Let's say that much. Yeah. So try to avoid that. You know, don't buy things in super big sheets thinking, oh, we'll just cut it down to a size where we can put it in a machine, because that is more of a challenge than you realize. Yeah. So a third point, large and or thin plastic parts. So if you design something that is bigger than the bed of a 3D printer, and you're like, you know, it's just a big shape made out of plastic, you know, some geometry that you can only get through 3D printing, but it's too big to put in a 3D printer, then you have a problem. So what you have to do in that case is cut it up into multiple parts and make sure to include some way of fastening them together accurately, and then you can print it in multiple pieces. Also, if you have a part that's like thin, like plates that are all like attached together, consider cutting them up into multiple plates and then laser cutting those plates or 3D printing those plates individually. Yeah. And just as a general point, tailor your geometry to the tool you're going to use. The first thing you should think about when you're designing a part is, how am I going to make this? That should not be the last thing you think about. So you know what tool you're going to use, and then you know what geometries that tool is capable of, and you design it with that in mind.
So speaking of that, here's some tips to this. Yes, give it. Okay, this can be either way. I thought I was gonna say put it in, keep it stupid simple.
It's fine.
Okay, either way, it's fine. So
we know you're not stupid, you're just fine.
Design your parts with the simplest geometry that will still be functional. So you don't need to go crazy on most parts. You can always simplify it down. If you have a metal part that in a robot that weight isn't an issue, don't make holes that look like they were done by topographical analysis to save weight, because you don't need to save weight. It's just going to be a pain to make those holes.
And if your robot does need to cut out weight, probably better to try to actually do topographical analysis.
Well, you can just do it with guessing and checking with FEA,
yeah,
but yeah, not ideal. Do not plan on using a more complex or challenging machine unless you need to. So, like we talked about a little bit, if you can make something out of acrylic or polycarbonate, but you could just make it out of acrylic, use the acrylic so that you can very easily machine it on the plasma cutter instead of needing to machine it on the Waterjet. Not the plasma cutter, laser cutter. The best machines to use are 3D printing is always good, pretty easy. Laser cutter, easy machine. If you can do something by hand easily, that's a good option. Drilling or using the mini mill or the mini lathe. We have easy access to this stuff. Good to use. The chop saw, it's a good idea if you have pieces you need to cut. And the bandsaw, if you have sheets you need to cut. If you can stick to these, that would be ideal. But we know there's some parts that you can't. So
yeah. All right. We have just one example. Ideally, we'd have a couple more of these examples, but just wanted you guys to get the idea. Here's a real life decision that we made. This is a part of Broombot. Some of you maybe have machined this part. So this is the part we needed to make. We knew that it needed to have this cylindrical thinner inside and then a flat plate on the edge to attach the wheel to the axle. So this could easily be one part, right? You can look at that and you'll be like, oh, it's this one part, you can just make that. But how are you going to make it? So what you could do for this is you could put it on a lathe. You could get like a really big piece of stock and you could lathe down this entire middle section. But then it's like that would take forever. You'd still need to you know, drill those holes. It's like you would just spend a lot of time and you'd waste a lot of material making that part. So the decision that we made was to split it into 2 parts, like we talked about for printing, is a good strategy for other types of machining as well. So now it's 1 part that's made on the lathe and 1 part that's a plate that we ended up plasma cutting before we knew that the holes were going to be too small. So that one didn't go quite as smoothly as we hoped, but still it was like we could just cut that circle out of material with a plasma cutter and it's easy. And then we added holes to attach them together. So they're fastened together now instead of being 1 piece. And they're just so much easier to make individually and attach together than making it as 1 part.
Right. You could also weld this, but the screws are just going to be easier. So now we don't have to deal with contacting welding people and making sure that our geometry works. No, just freaking screw it.
Yeah. So there you have it. These are the kinds of decisions that it's helpful to keep in mind, helpful to make as you're designing. I think that's all we have.
That's all we have.
All right, yeah, that was a lot. We're just like 2 minutes over time, so we got it done now.
If we hadn't had Zoom issues.
If we hadn't had Zoom issues, would have been super, super easy and short. All right, so we can take questions if any of you guys have questions. I can also monitor the chat if anyone in Zoom has questions.
Yeah. Where can we get the Dremel? There's one in the. Where can we get the Dremel? So there's a Dremel in a drawer in the ASME Lab. It's underneath where the heat shrink is, like by the screws. Yeah, bottom left. It says Dremel on it. Yeah. There's a couple in there. I don't know if all the tools will fit in all of them or if they'll work. But there's at least one in there that works.
There's a really good one in Boelter.
And there's one in Boelter Makerspace.
This is on the table with
yeah. There's also more bits in the lathe, in the mill drawer. There's more like metal type bits in there. If you wanted that.
Someone's asking you guys a link to the slides. I think we'll probably send out the link to people who signed in, or maybe everyone. I don't know.
Yeah, no, we'll send it out in next week.
We'll send it out in the newsletter as a recap.
Yeah.
Yes. It's in the ASME drive right now. You can put it somewhere that's more accessible.
No, where to put it. It's in the Office of Resources, just the Office of Resources folder. But I don't know if everyone has access to that. Oh, that's a good idea. It should go in the Notion. Right. We'll do that.
That'll also probably be in the newsletter recap.
Yeah, it's like 20 pages and there's no pictures in it. So that's why we decided to make a presentation that wasn't that much. I mean, that still took an hour, but it's not 20 pages.
Anything else?
Yeah, if you come up with anything, if you talk to me, talk to Rebecca, talk to Alyssa, talk to Aaron, talk to your tech leads, talk to Zach. We know what's up. Okay.